All right, Kines 415, this is going to serve as your lecture for Friday. You still have old lectures, but I thought I'd kind of use this to kind of splice some things together, make sure we're all on the same page. Just trying to be a better teacher, better communicator. So the first thing I want to talk about is chains. So we kind of been a few days talked about chains and kind of how did that term come from, and it's used a lot in kinesiology. Wednesday it made me think of like the kinetic chain, and I know like kinetic is forces, but forces influence motion, so you can understand how they kind of go back and forth. So the kinetic, like the anterior chain, the posterior chain, muscles in the front, muscles in the back. But chains in terms of movement are either open or closed. And the openness or the closedness can be viewed in either simultaneous or sequenced motion, which we've spent a long time kind of talking about. So what we're looking at is the distal segments, hands and feet, specifically, because those are our influencers of work and movement, right? Most of the time, right? Hands and feet are going to get us places, going to do us things, okay? This seemed to work with students, so in case you were running late or didn't come, things that swing are sequenced. So if you just look at the clock hand swinging back and forth, that would be sequenced motion because it's just one movement. And so notice that angular context of when we just move one thing at a time. The angular context, like you would be on a swing, right? When you're swinging, angular, very angular. So in the past when I've used things like angular, that's what I mean, the swing. Is it free? Is the distal segment free to swing? If the answer is yes, then it's open to sequence motion. So my wrist is open to sequence motion. My elbow would be open to sequence motion. My shoulder would be open to sequence motion. So it's like sequenced motion has its own closed and open, its own yes or no. Well, Campbell, how would something be closed to swing? Well, if I put my hand on this book and used friction as a closing of the road, thought that might work, I can no longer swing freely. I can no longer swing openly. Does that make sense? So that's kind of the key. Is it free to swing independently? I don't know if you guys are going to be able to see my knee, but I can swing, let's see, I can swing my knee. It's open to sequence motion, but if my foot was on the floor, let's see if you guys, oh, Mr. Table. That's why I use props. Okay, so we have a celebrity in the house, guys. Thank you, Barbie movie. We have Mr. Kendall. And Mr. Kendall serves as, when I'm trying to teach shoulder movement, I could use Mr. Kendall as a humerus or as an ulna. Or in this case, we're going to look at his feet being on the ground, right? So now his feet being compressed into the floor, his distal segment isn't free to swing. His knee can't swing independently. His hip can't swing independently. Right? We closed that sequenced or swing road. Right? The other is shift, simultaneous motion, where if we have two sequenced motions done at the same time, it's no longer a sequence. A sequence is one step after another, and you can have a step of one, but when we have two things happening at the same time, they can cancel out each other's rotation and summate each other's translation. So is the distal segment freely able to shift? In the case of my hands, like doing this, I am free to shift. So therefore, my simultaneous road is open. I am also free to swing. I can just swing my elbows. I could just swing my shoulders. So that's why this would be open, open. Open to shift, simultaneous, and open to swing, sequence. If I was doing a squat, like an air squat or a rack your weight squat, my feet are closed in terms of simultaneous motion of my knees and hips and anything else isn't going to produce a shift of my distal segment. If I have enough force to overcome the weight, it's going to produce a simultaneous movement of my proximal segment. But my feet are closed. I'm not going to go straight down. In addition, because of friction, my feet aren't allowed to swing. Hopefully, I don't want to swing, hurt myself. I don't want to move just my knees or just my hips when I'm doing a squat. So I definitely want to close the sequenced roads. I want it to be closed, closed. Closed to shift, closed to swing, closed to simultaneous, which it's not closed to simultaneous movements. You still have simultaneous movements. It's closed to those simultaneous movements shifting the distal segment, hands or feet. It's closed to angular movements swinging the hands or feet independently by themselves. Does that make sense? Distal moves about proximal, proximal moves about distal. Okay? So I hope that helps clear that up. So let's walk down the path of where we're leading, okay? Kinetics and kinematics. I said something Wednesday and I thought about it. I was like, ugh. Kinesiology. But some people pronounce it kinesiology. So technically, how you pronounce it is what you're studying. Because if you say kinesiology, kinetics is force variables. So kinesiology could technically, nerd alert, be like the study of human forces. But it's all different forms of the same thing because it takes forces to influence motion. Motion is influenced by forces. So those things are kind of interchangeable, and that's how we know. Is remember, the equal sign is just relationship to. These are interchangeable things. They're related to each other. This goes up, that goes up. This goes down, that goes down. You need this to influence this. Cause and effect. F is equal to ma. Forces influence motion. Kinetic variables, gravity, muscles. We're very interested in the muscles. Kinetics influence movements of objects. And if you say, well, wouldn't those forces be coming from objects themselves? Yes. But this isn't about that object yet. This is about whatever object we're looking at, whether it's you, the dumbbell, the baseball, the bat. And we have to look at all the different forces influencing that baseball, bat, or you, whatever object we're looking at, and how all of those outside objects' forces can mess with its change of motion. And then if we want to look at those other objects, no problem. But we have to do F is equal to ma for each object, if that makes sense. God, this computer's driving me crazy. Power saver, power saver, power saver. I get it, man. Gotta save that power. All right, we saved the power, you guys. Yay, we did it, we did it, we did it. Was that Dora? We did it, we did it, we did it. Yeah, John Stamos, we did it. I forget. So, this is not meant to, maybe the chain stuff is new introduction, and I told you in my shortened micro lecture the exact questions I'm going to ask you on the test. It's to introduce you into a world of mechanics, of engineering, and how we can use some of those principles to apply it into biomechanics or kinesiology. Introduction. Not asking you to analyze crazy stuff. I just want to introduce you to this stuff. These are things you should have been introduced to already that I'm just developing into layman's terms. How would we use it? What does it mean to us? So here I have the swing sequence, shift simultaneous. So work. The reason understanding work is important is because you have to have work for power. The reason understanding power is important because if I tell you that simultaneous motions done in sequence is advantageous for power because you have a little bit of force, you have a little bit of speed, you kind of play, then we kind of have to know these equations, not to solve for them, but just to kind of understand how different things affect other things. So what is work? Work is, technical definition is force times displacement. How far did you move something in a specific direction? So displacement is a vector. This is the one that I told you in class I have a problem with, because force is, think of it more as the resistance that you're doing. We are providing the force, but what is my resistance? What's resisting my force? My muscles working through what's representing them on objects, which is usually my hands and my feet. So let me give you an example. If I'm looking at the work I do on a bench press, and let's say, because I'm getting old, let's say I'm doing 135 pounds, okay? I'm trying to make this make sense to all of us. Doing 135 pounds. And I'm going to get it from A to B. So I'm going to have a displacement, a vertical up and down displacement. So what the work equation says is that the work I did on the barbell with the weights, I displaced the barbell and the weights. That's what I actually displaced. So the force isn't what I'm giving it, because that could be variable. I could push it up real fast. I could do it real slow. Technically, if I had like force sensors, the one where I push it up real fast, I would be producing greater force than if I do it real slow. But yet, the work would be the same, whether I do it fast or slow, because it's not about what I'm giving it. It's about what it is. It's the resistance. It's 135 pounds. It's the resistance. And the work is the resistance times the displacement, regardless of how fast and slow I did it. The work would be the same. Another example before I get back to it. If I can't, well, maybe one lap around the track upstairs, because that's short, but I can't do it anymore. But I used to run the 400 meters a long time ago. Whether or not I run around the track one time with all the force I have in my body, I give it all the force. My work is the exact same if I jog real slow, because the force is really my resistance. It's my body weight. It's my mass. And so the work would be, how much did I displace me? Not necessarily like what I'm giving the ground, what the ground's giving back to me. Okay, so substitute or just be aware that force is the resistance that we're doing. What are we actually moving? If you're moving furniture, it's the mass of the furniture. And times the acceleration of gravity, whatever, that's what weight is. But it's the furniture. If you're moving the furniture, it's not necessarily how hard you're pushing the furniture. It's the resistance of the furniture and whatever the friction is going to be across the floor or lifting it up. Okay, it's the resistance. Now, power. I told you power lies in between force and speed. And that's what work has force in it, resistance. Resistance is still a force, guys. So the work has the force component, and the time is the speed component. Not necessarily time means you're going fast, it's just time allows us to categorize how fast you're going. Time allows us to slot the speed. I mentioned this on Wednesday. You don't report your speed in the 40-yard dash by saying, how fast did you run in the 40? Dude, great, man. 18 miles an hour, average. Well, what was your peak? I peaked out at 20 miles an hour. Nobody does that. We give our inference of speed with a measure of time because we're all displacing the same. We're all displacing the same. Our resistance doesn't matter. In other words, a 40-yard dash for a 300-pound person, it's an absolute, it's not relative, versus a 40-yard dash for a 150-pound person. Right? When I say it doesn't matter, the time doesn't matter. Like we don't, the work would be different. The work equation would be different because they'd have different resistances, and the power equation would be different. But in terms of reporting who's faster than who, we don't take that into consideration. It's who's faster. I said this on Wednesday. The fastest man in the world or the fastest woman in the world isn't relative to body weight. They don't say, well, this person came out second in the 100-meter dash in the Olympics, but because they weighed more, they should get the gold because they did more work and they had more power. That's not how this works in some events. Okay? So let's get back to making sense of this. So power is how much time did it take you to do the work? Work over change, that's what delta is. Delta is just change. The change in time, how much time it took you. I prefer layman's terms to read it as power is how much time did it take you to do the work. And because there's a time factor, time is of the essence. What do you think that means? Like, gotta go, gotta move, right? We're on the clock, time. So sequenced and simultaneous motion combine to form power. Now, every type of motion that we have technically has these concepts in it. If I move, something had to move me, so there was work. And how much time did I do it? There's power. So we're using these not as a solve for X, but just kind of an understanding. And when we get into muscles again, like we did in 310, you'll remember that I used contraction interchangeably with work. I use those two terms interchangeably. And that is because, right, muscles influence motion through the context of contraction. Okay? So muscles are influencing resistances. That could be our body weight or exercises, right? Muscles influence these resistances. Muscles influence the motion of our bodies and joints through the context of contraction. How much time it takes for our muscles to influence our motions through the context of contractions. Power. Okay? Now, this thing, I tell you. All right. Let's walk it down and see where we're going with this. We have kinetics and kinematics. Kinetics forces, kinematics movements. We have scalars and vectors. Scalars are magnitude only, vectors are magnitude and direction. In class on Wednesday, I emphasize the difference. Scalar is just a number. A vector is, where's that number going? Scalar quantity would be $100. $100, $100. A vector quantity would be, who owns that $100? Is it mine? Is it yours? Did we have a transaction? Did I give you 100? Negative 100 for me. But then you gained 100, positive 100 for you. Okay? So directional magnitude is the definition of a vector. Okay? Point of application, we talked about the sense. Senses, there's different forces, pushes, pulls. We're going to talk more about friction on Monday because friction's so important. And then we went into the different types of vectors, the different types of meaningful magnitudes. And we talked about how long, and this is a review, hopefully from high school or basic physics, like longer arrows represent bigger vectors. Where, if direction matters, well, that's what's telling us direction. And we're going to have our Cartesian plane and all that stuff coming up. But here is the, in my opinion, the important thing is that we have, let's say, 0 or positive x, positive y, negative x, and negative y, right? 90, 90, 90, 90. The important thing is that for my vector, my muscles are vectors. They're force influencers, so they're forces, and they pull on bone. It's impossible. I say impossible. It's highly unlikely. I guess technically it would be impossible. Yeah, I could say that. It's impossible for that muscle to only pull in one of those 4 directions only. Because a muscle has to go into a bone. It has to have what we call an angle of inclination. It has to go in at an angle because the only way it couldn't is if it was like a non-contractile ligament that just like literally went in one bone and out the other bone. And that's not a muscle. So the point is that you have these vectors, and sometimes they are in the same direction, about the same point. We could add, subtract, like balance in the checkbook. You made so much money, you spent so much money, you have these positives, you have these negatives, and they're all apples and apples. Transactional money into your account. What a concurrent vector is when you have a resultant or a big force happening at an angle that's in a combination of x and y. You have one force, but it's in a combination of x and y. Or if you can't imagine forces, I take a baseball, and instead of throwing it 0, 90, 180, or 270, what if I threw it 45 degrees? Well, some of that velocity is y, and some of that velocity is x. And as I told you, when we do this, it has to be directional dependent. X forces can't influence y motion, and y forces can't influence x motion. If you're moving furniture, picking the sofa up isn't going to get it across the room. It's as simple as that, right? So what happens if we have a resultant, a force or a velocity that's in a combination of x and y? We have to extract the x and y components. We have to take the fruit salad and make it into apples and oranges so that we can compare the apples, the x, and we can compare the oranges, the y. So it's important to understand what concurrent vectors are. Basically, they're where a resultant happens and the y, let's see if I could do this, and the x component are two different components happening at the same place, the same point. And they're going to be perpendicular to each other because x and y is perpendicular to each other, and that's why we can do trigonometry to extract our x and y, to extract, hey, we have this fruit salad, but how much of it is apples, how much of it is oranges? That's what trigonometry does for us in biomechanics. It allows us to do this with all of the X forces that are going to influence X motion, and all of the Y forces that are going to influence Y motion. So a couple examples of these concurrent forces. Because we love muscles so much, I thought we would start there. And that's just looking at how you have a muscle, right? Looks like a deltoid muscle, and it's pulling on the humerus at an angle of inclination. So it can't, every muscle, again, can't go straight. It could be steep, it come in steep, but it has to be in an angle. And what I wanted to show you through concurrent forces is that some of that force, so this would be the resultant, and some of that force is trying to pull this bone into that bone. We call that a stabilizing component. You know, people think of just ligaments stabilizing. Muscles stabilize joints a lot more than ligaments. Ligaments help stabilize, but if your muscles aren't contracting to stabilize the joint, that's why women typically have more ACL injuries than men. It's not a ligament issue, it's a muscle issue. Look it up, it's called muscle stiffness. Typically men, more testosterone, we typically are stronger with our muscles. Well, guess what? They help us stabilize more. Typically women have more range of motion, they're more flexible because they have less muscle tension. And so that's the trade-off. What you gain in stability, you lose in mobility. Okay? So we're also look at this other component, this perpendicular component. That's going to be our rotary component. That's what's actually going to help us move because it creates a torque. So I'm not asking you to memorize this stuff now. We're going to get into this more in muscles, but I'm just trying to show you how you can have one force pulling on one place, but have two different purposes or functions that are perpendicular to each other. The class example I gave was like a standing long jump, where if you're trying to do a standing long jump, you're trying to go across, but in order to go across, you got to go up. True? To go across, you got to go up. So when you drop down and push off of the ground is going to push at you in a combination. Fruit salad, apples and oranges, is going to give you some apples, is going to give you some oranges, and the combination of those is going to look like this. It's a concurrent force. You have this and this friction pushing you this way, and the normal force or the direct compression, the macro compression pushing you this way. And the combination of these two individual fruits happening at the same time gives you fruit salad. Okay? So we can't add this and this. We can't add the friction plus the compression to give you this. We can't do that. Why? This is why, literally, like this is why. We can't because X forces don't influence Y motion, and Y forces don't influence X motion. So we have to extract, when we have something that has a combination, we have to extract what is the Y component, what is the normal force, what is the direct compression, what is the push that's influencing my motion up, what is the friction, what is the micro push, what is the X, what is that force that's influencing my motion across. So in the real world, we have all of these resultants, we have all these combinational forces and movements, and my job is to teach you that all of those combinations are made up of apples and oranges, and we have to extract those apples and oranges so that then we could apply our basic physics to them. Okay? So again, I can't say a Y force can influence an X motion changes in motion. So that's why. Okay, somebody's trying to call me, but I'm working. Give me 1 second. All right. So what that is walking us down is trigonometry in biomechanics and kinesiology. Okay? Remember, this isn't about solving for x and y. This is about understanding the things that make up the x and y. So here's our example that I gave you. Again, you have a muscle pulling at a given angle. Some of that pull is in the x, some of that pull is in the y. Those are two different functions. The x component of that muscle's pull isn't trying to rotate me. It's kind of crazy to think, huh, that your muscles are pulling, but not all of that pull is trying to produce joint motion. Some of that pull, a lot of that pull, think of it like this. If you take dumbbells off to do like shrugs, and it's heavy, and so you have this dumbbell, don't you feel like your arm muscles puffing up, even though you're not necessarily working them? Because when you have a dumbbell in your hand, especially a heavy one, it's trying to dislocate your wrist. It's trying to pull your wrist apart. It's trying to pull your elbow apart. It's trying to literally pull your ulna from your humerus. It's trying to pull your humerus from your scapula when you have a heavy dumbbell. So one reason you feel all those muscles puffing up, even though you're not actively trying to recruit them, is stabilization, preventing this from falling down, preventing this from falling down, and preventing that from falling down. Okay? So just like on the vertical jump, you had two different forces in two different directions that were serving two different masters, that were doing two different things. The friction was influencing your motion across, and the normal force or the macro push was influencing your motion up and down. Very similar. When your muscles are pulling, whatever the component is into the bone is going to be a stabilizing component, and whatever component that's perpendicular to the bone is going to be a rotary or a motion component. Not all of that muscle influences just motion. That's pretty cool. Okay? So that leads us to the relationship between sides and angles. Remember, the reason trigonometry works is because, trigonometry, the study of right triangles. Well, x, y, and z are always perpendicular to each other. So we're always going to have a right triangle with our apples and oranges. It's crazy. Maybe apple and orange isn't a good example because they're round and not straight. So maybe I could come up with like silly carrots and celery or something, where like you make them perpendicular to each other, but that's kind of silly. So because every vector is directional, and it could either be all in the x, great, x forces influence x motion, x motion is influenced by x forces, all good. All in the y, that's so silly. Good. Y forces, Y motion because of Y forces. But think about how rare that is. Think about how hard it is to give. Remember, it's hard to be accurate. Think about how hard that is to give any force or any movement all in the positive x, positive y, negative x, or negative y. Odds are it's going to be somewhere in the middle. Here's a better way to look at it. 360 degrees of options to apply my vector. And there's only 4 options where there's not a combination. And that's only in 2 dimensions. In the z, then it's even harder. But think about it. All here, and then I have 90 options to be some kind of combination of x and y. All here, then I have 90 more options to be a combination of x and y. It's hard to not be in a combination of x and y. So whether we're talking about let's say a basketball goal. Ken, you're going to be a basketball goal right now. and you have a basketball goal and it's laying down and you got to raise it up so that you could shoot some basketball with your kiddos. All of that 10 feet from the base to the rim is in the X. All of that 10 feet, you get it erect, is in the Y. But as you raise it up, it's going to get less and less and less X and more and more and more Y until it's all the way Y. If you lower it down, it's going to get less and less and less Y and more and more and more X until you lower it down. The distance is the same, the scalar distance, but the displacement, the vector displacement changes. It gets less and less and less across and higher and higher and higher and higher. And that's what trigonometry is. Trigonometry is the understanding that the X and Y components, the displacements, are proportional to the angle changes. It's impossible in a right triangle, an X and Y, for me to increase the Y and not decrease the X, or to increase the X and not decrease the Y. You have to change the angle. So that's what trigonometry is. That's all it is. It's the relationship between the apples and the oranges, the X's and the Y's, and the angles that change them. Okay? So as a refresher, we have sine, cosine, fancy words for ratios, proportions, percentages. So I'm going to show you how, when we say, okay, Ken, the basketball goal, who's Ken, rotated 45 degrees. Well, 45 degrees is halfway between 0 and 90, right? So what I'm going to show you is that when you do 45 sine or 45 cosine and you get the same number, it's because the percentage of Ken, when he's halfway, the percentage is the same for both. The percentage is the same. Here's another way to, hopefully, to understand what I'm trying to say. If Ken was at, you know, sometimes a basketball goal, after you dunk on it, I wouldn't know what that's like. You dunk on it while it starts to lean forward. So let's say Ken was 85 degrees from the horizon or from 0. Doesn't that make sense? He's taller than he is long or across. He has more Y than X. So if he's 10 feet and he's 85% to 90, his Y component is going to be a lot more than his X component. That's all that is. That's all that is. So when we do the trigonometry, the Y component percentage is going to be a huge percentage of 10 feet. And the X component is going to be a very small percentage of 10 feet. And then once we have those percentages, and you know what you're going to see those percentages are in your calculator is decimal places. But that's the same thing. Just move the decimal place over 2 times and that's a percentage. That's all it is. So I'm going to teach you how to use common sense to say the basketball goal is shallow. My X percentage of 10 feet is going to be super high. And the Y is going to be super low percentage. And as we raise him up, the Y percentage is going to get greater and the X percentage is going to get less. And the reason you cross multiply, that's just because once I have a percentage of a given side, X or Y, I have to multiply it by how long is Ken? How long is the basketball goal? What's the actual magnitude of it? You know, 90% of 10 feet. 10% of 10 feet. That's all that is. If we're using velocity, I throw a ball 75 miles an hour at a certain angle, the resultant 75 miles an hour, but that 75 isn't traveling 75 in the X or in the Y. In other words, it's not traveling 75 miles an hour up or 75 miles an hour across. It's traveling in a combination. And so I need to extract the apples and the oranges. I need to do trigonometry. And to say, okay, what if it's very shallow? I throw it very shallow. Then I know my X percentage is going to be a lot higher than my Y percentage. And if I throw the ball very steep, I know my Y percentage of whatever that speed is going to be more than my X percentage. And the X and Y component is actually going to be the percentage, the decimal place when you do the sine and cosine fancy stuff, times what the speed is. And then those numbers are going to be the components, the directional components. That ball thrown at this speed, at this given angle, is traveling this fast in the up and this fast in the across. And then once we have the up and the across, then we can do something with it. Because I can't do this with apples and oranges. I can only do this with apples or the oranges. I can't do this with fruit salad. We have to extract the x's and extract the y's, then we can apply our concepts to it. Okay? So I'm walking you down a path of how we're going to get and why we're going to get to this. The Cartesian plane. And that's just practice examples, just to show you the concepts that we're going to do. But on the test, you're never going to have to solve for x, but you're going to have to understand how x's and y's are influenced through resultants. And I'm going to teach you that, and we're going to practice that, okay? So hopefully that helps walk us down where we're at right now. And I hope you guys have a safe weekend, and we'll see you Monday.